Okay, so electric potential energy. I would love to call it EPE, but I've already used the acronym EPE for elastic potential energy. So maybe I should have called that spring potential energy, but I didn't. What physicists call it is they use capital U for potential energy, and so elastic potential energy would be called um, spring potential energy U subscript S. But that's in the past. Okay, so we have electric potential energy. We call that UE. Capital U stands for potential energy. The subscript E stands for electric. Okay, let's first of all talk about GPE. GPE is also called symbolizes capital U subscript G for gravitational potential energy. To have any kind of potential energy, you have to have two objects at least. So, so we don't talk about the potential energy of one object by itself. For example, a rock that you're holding above the surface of the earth. Okay, that rock does not have potential energy unless the earth is there. So you need two masses for gravitational potential energy. So the electric potential energy requires at least two charges. So you need one of those charges is like gravitational. To be significant potential energy, you have to have at least one of the charges being big. We call that a field charge. And then you have a small force called a test charge to test how strong the electric field is around that field charge. So you need, and we talk about the electric potential energy of the system rather than the electric potential energy of one of the charges. You need two charges, just like you need two masses for gravitational potential energy. Okay, don't forget energy is a scalar, so you don't need directions like you need for field or force. Electric potential energy is a little more complicated than gravitational potential energy because you got charges that can attract each other or repel each other depending on their charges, their signs. For gravitational potential energy, you only have attraction forces. Gravitational force is not repulsive, it always is attractive, but electrical forces can be repulsive, pushing away each other or attracting each other. So here's the basic idea. The farther two like charges are away from each other, the bigger the R, the distance between them. If they're like charges, the lower the EPE. So if you have a big R, and they're like charges, no matter if they're both negatives or both positives. Like in this case, we have two positive. So if they're like charges, the bigger the distance between them, the R, the smaller the electric potential energy would be. Okay, so there's that inverse proportionality. Actually, it's to R squared, but we'll find that out later. Okay, so if you get negative charge, the closer the R's, the higher the potential energy. So that's a very important concept. Okay, just think about this. The closer they are, the more they want to push away from each other, and there's more energy in that system. It's like a compressed spring. If you put two negatives close together, they want to push hard away from each other. They have a lot of energy stored. As soon as you release them, they'll fly apart from each other. And that electrical potential energy will turn into kinetic energy. But if they're far apart, there's not really a big force pushing them apart. So there's very little EPE. In the same way, unlike charges, if you have plus and a minus, the closer they are together, when released, the less kinetic energy they'll have when they smack into each other. So the closer they are, the less electrical potential energy they'll have originally. So as R gets bigger, it's like pushing a rock further away from the Earth. The GPE gets bigger. Well, the electrical energy will get bigger as well. But that's for unlike charges. It's the opposite of when it's like charges. We're not going to make a big deal about the work and relating it to electrical potential energy, but work is the change in energy, in this case, in electrical energy, potential energy. And that would equal UEF minus UEO, original. So look at this picture right here I drew. If I take two like charges that are very far away from each other, that means the work I do to push these two like charges together is equal to the electric potential energy I give the system. So it'd be the final minus the original electrical potential energy. But the original, if it's very far away, the original electric potential energy is 0. And the final electric potential energy is something big. So a big number minus 0 is always going to be positive. So I do positive work. An external force does positive work in order to bring two like charges together. Closer. Okay, this is external work. I'm working against the field. These positive particles or these like particles don't want to come. They resist coming closer together. So the external work is positive. The work I do to push them together to give them more electrical potential energy is positive. It's external work. Now, you can say that the electric field is doing negative work. when this happens. But we'll stick to what external work is. Now for unlike charges, work is equal to change in U, electrical potential energy, but N is still U, EF minus U, E, O. Okay, that's conservation energy. It still applies as it did for light charges. But let's see. What if I pull or push two unlike charges together? Okay, so I'm pushing two unlike charges together. Now, I really don't do any work when I do that. The field is doing work. The electric field is doing work. So why is that? Well, if I bring them from very far away to closer, when they were far away originally, unlike charges have more. Whereas if I brought them really, really close together, this would be a small. If they're touching, it'd be 0. But if I brought them closer together, like my picture is showing, this would be a smaller number. So you can see that in this case, the work is going to be a small number. That's a big number. It's going to be negative. Work is going to be negative. So negative work is done by an external force. To bring two unlike charges together, closer together. Positive work would be done by the electric field, but negative work would be done by an external force. Okay, highlighted in blue up here is in the upper left-hand corner is the equation for the electrical potential energy of a system of two charges. Okay, so it looks like Coulomb's law, right? Force equals K cubed Q or R squared, except there's only one R in the denominator. So when you take away one of those R's, you got what the electrical potential energy is. Okay, so if they're like charges, and when you're using this equation, you're supposed to keep the signs. Keep the signs. Keep the signs on the charges. Okay, so if they're two positive charges, it comes out to positive work. If it's two negative charges, right here, it comes out still to positive work, like I was talking about on the previous slide. Okay, so now as you increase as you move them closer together, the R would get smaller, and therefore the potential energy would get larger. So you can see that potential energy of a electrical potential energy of two like systems will increase if objects get closer, the R gets smaller. Using that same equation, if you have unlike charges, the signs will be different. Right here, signs are different, and so you'll get a negative electrical potential energy for the system. Okay, so this is when you have opposite charges. So the potential energy of the system decreases as the charges, unlike charges, move closer to each other. So as R decreases, the electrical potential energy becomes a bigger negative number. Okay, this is like kind of goes against what we said at the beginning of the year. In this case, a bigger negative number would mean a smaller electrical potential energy. A bigger positive number would mean a bigger electric potential energy. So that's kind of confusing. So the way I think about it is like a rock and the earth. This is an attractive force, gravitational force. And obviously the closer the rock is to the earth, the smaller the electrical potential energy. Same for if you had two unlike charges. The closer they are, the smaller the electrical potential energy. So here's the concept, again repeated here, about the types of charges in a system and the sign on the electric potential energy of the system. So if you have like charges, like I said before, that's positive electrical potential energy. But if you have unlike charges, you're talking about negative potential energy. And basically, again, that's because you keep the signs when you're solving for electrical potential energy. You keep the signs on the charges. So here again, if you had to do work to push something, two charges, in the direction that they don't want to go because they're repelling each other, you're adding electrical potential energy to the system. And were you to release these two objects, that electrical potential energy would turn into kinetic energy as the two charges flew apart from each other. The electric potential energy would be turning into kinetic energy. The electric potential energy would be decreasing as the kinetic energy increases as they fly away from each other. Okay, if we have unlike charges, it's the same idea. These two charges want to move closer together. If you push them apart, you increase the distance between them. You have to do work to do that. And your work, external work, is turned into electric potential energy stored in the system. If you release these two objects from their positions, they're going to spontaneously come together, closer together, that electric potential energy will therefore transform into kinetic energy. The electric potential energy would decrease, the kinetic energy would increase as the charges move towards each other. Okay, so we got two plus charges, so like charges. What is the sign? Electric potential energy of the system. So, I mean, you could memorize it, or you could use the equation. And since both these are positive, you're supposed to keep the signs on the charges. The electric potential energy will likewise be positive. Okay, here we have two like charges. How would the electric potential energy system change if the distance between them is doubled? Well, it doesn't matter what kind of charges, the same thing will happen. Whether they're like charges or unlike charges. So, if you're going to double the R, this will go to 1/2, not 1/4. Now, if that was unlike charges, let's say this is plus Q, and this is negative Q. That's R, the distance between them. If I doubled the distance, this would double the electrical potential energy. Because now they're twice as far from each other, just like if I doubled the height of a rock off the ground, it would double the GPE that it had. So you can't really use the what if equation that you did up here when they're unlike charges. You gotta use concepts. And I can explain it in a complicated way, but it's better to use concepts than to do the equation and figure out why it's the opposite. Okay, so if I push a plus and a minus together, what happens to potential energy? Well, it's like bringing a rock closer to the ground. The GPE is decreasing as the rock gets closer to the ground, because why am I using the GPE thing? Because it's like the rock and the earth are like opposite charges. They attract, but it's not charges. It's gravitational force, which is only attractive. So I don't really have to even push it. I'm just allowing the electric field to pull it closer. So when you get unlike charges and they're coming closer, the electrical potential energy is decreasing and the kinetic energy would be increasing. In this case, I'm not really doing any work. The electric field is doing positive work. Okay, so this little Q plus is attracted to negative, so they're opposite charges, unlike charges. So the test charge, the plus Q, little q, will spontaneously move towards the negative plate. When it does that, its kinetic energy won't be increasing because it's getting faster and faster, but its EPE, that energy doesn't come from nowhere. That kinetic energy comes from the EPE. I'm sorry, the U E decreasing. So, okay, the change in U electrical equals U EF minus U E original. So that'd be KQQ R F minus KQQ R original. So basically it'd be K. Basically be that. And so RF minus RO would be 3R minus R. And so that'd be 2R. So we get KQQ or 2R. Now, it decreased because these are like charges. It decreased when you get two like charges further away. So I'd have to put a negative on that. So all these answers are wrong. Now, if I said, so all these have to have a 2 there. They made a mistake. So my correct answer would be letter D. Now, if it was a positive Q and a negative Q, it'd be the same answer. But it would have increased. It would have been an increase in the electrical potential energy to twice as much of what it was. Okay, because it flips around. Okay, these are easy because instead of doing the change in potential energy, we're just finding the potential energy. So UE equals KQQ over R. So K is 9 e to the 9. That's Coulomb's constant. Q1 is 5. Milli stands for e to the negative 3 times the other one is 2.5. They're both positives, so that's important. And the radius between them, 3 minus a negative 8. The distance is 11 meters. So when I calculate this out, I get 10,227.2. Okay, and then that is, let's see, 1, 2, 3, 4. So that'd be 1.02 times 10 to the 4 joules. So you do same thing with this problem. You can look up the QR code if you want. But in this case, when you do U equals KQQ over R, you got to keep the negative. So Q1. So your answer is going to be negative. So it's the same thing except we got negative. Okay, this one's just like the first one we did. So we got two negatives. And so when you find UE the two negatives will cancel out when you multiply them to be a positive. And that's why all these choices are positive. Check the QR code for the answer. Okay, we can see that one charge is positive, one charge is negative. So the UE, the electric potential energy is going to be negative. Since they're plus and minus charges, they're going to attract each other. So this one can't be true. There's no force holding them from moving. They will move together. So that one's false. External force must act on a charge to prevent them from getting closer together. Yeah, because they want to. So that's one choice. Decreasing the distance between the two charges, plus and minus, increases. No, that decreases. So that's not it. Substituting each charge with the same value but opposite signs will have no effect on the calculate. Yeah, that's true, because if you switch these two signs around, that's not going to affect either the value, the magnitude, or the sign. So that one's correct. Now, electrical potential is not electric potential energy. So this is kind of confusing. Sometimes they just call this potential. But electric potential is what we call voltage. And it's given the symbol delta V. So basically, here's the equation for electrical potential, otherwise called potential, otherwise called voltage. So a volt is a joule per coulomb. And I like how they said this here. A volt is the work a battery does to move 1 coulomb through a circuit. Okay, so here's the battery. Let's say it's a 6-volt battery. You got a plus and a minus terminal. You connect a circuit to that battery, a wire. Electrons will be pushed through the wire by the battery. The battery will do work to push the electrons through. So a 6-volt battery will do 6 volts, 6 joules of work per coulomb of electrons being pushed through. So a 6-volt battery is the work. 6 volts is the work that the battery does in pushing the electrons from one terminal, one place in the electric field, to the other terminal. And that will make the whole idea of what potential difference a little less abstract. So here's yet another equation. Since potential difference is a change in electrical potential energy over Q, we can rearrange this, knowing that the change in UE is the work done by like a battery. So we can change that to change in V equals work that the battery does to push the charge over the charge that is pushing. And then we can rearrange that to the work is equal to QV, or work is the change in potential energy of the system. So what is the change in V? This is the distance. We use R for that. From a charge of 6.23. Okay, well, this is like the field charge. This would be like one of the terminals on the battery. So I'm going to call that capital Q. So V equals, we got several equations, but probably this one would be the best. Okay, so that equation was given as 1 for voltage. Okay, so 9e to the 9 times 6.23 e to the negative 6 over 5. So I get 11214, which is 1.1 e to the 4th. This is the same idea. You got V. You're looking for change in V. This is the distance away R. This is Q. So change of V equals K Q over R. But because the K is negative, this is going to make the delta V negative. You got to put the signs in for this stuff. So you can look at the QR code to figure that one out. Okay, so how much work is done by an external force on a 10 microcoulomb charge? So that's little q, because he's moving from point C to B. So point C is 0, and point B is 150. So the change in V is VF minus VO, potential F. So that'd be 150. So that'd be a positive 150 volts. So best equation to use here would be work equals QV, because that's what the things we have. So work equals Q, 10 microcoulombs. Micro means 10 to the negative 6 times 150 positive. So this comes out to 1500 e to the negative 6, or 1.5 e to the 3 e to the negative 6. You could use your calculator. 1.5 e to the negative 3 joules. Okay, here's the same kind of idea. Little q, negative 10 e to the negative 6. Don't forget to keep the negative sign. How much work is done? Point C to B. Okay, why do I keep on doing the same point? So C to B, we already did this the other day. The other slide, changing V is final minus original, so it's 150 volts. So work equals Q times V. So it comes out to negative 10 e to the negative 6 times 150. So that'd be negative 1500 e to the negative 6. And if I put that in scientific notation, like I did before, joules. Now, just remind you, when you have a parallel plate, also called a capacitor, these are the field lines. Okay, it's a uniform field between these two charged plates. Now, a battery basically is like a capacitor. Okay, I'm just highlight the parts that are important here. This is a uniform electric field between, this is called a parallel plate, or it's called a capacitor. And battery is very similar to this, with this being the plus terminal and this being the negative terminal, and the electrons moving in the battery because of the field inside the battery. Okay, the two plates always have equal amounts of charge. One's charged positive, one's charged negative. Okay. They're parallel. The electric field between the plates is uniform, but outside the plates, there will be no electric field unless it's connected by a wire. Then the electric field will pull the electrons through the wire to the positive plate. Okay. Another name for parallel plates is a capacitor. Okay, so we know that the direction of the field is always from plus to minus. And if you think of a positive charge, Q plus, from what we learned before, when that Q plus is up against the positive plate, we got maximum electrical potential energy for that positive test charge. But when it's right here against or very close to the negative plate, we have 0 electrical potential energy. So the change in V between the two plates, the voltage difference between the two plates is the change in U for that given charge. So basically, the negative plate 0 UE, so this would be the U of the positive plate over Q. So this would be whatever the voltage is. This would be 0 voltage. The potential at the negative plate would be 0 volts. Potential at the positive plate would be whatever the voltage across the plates is. So this question, what generates the electric field between the two parallel oppositely charged plates? Well, electric field is caused by the different charges next to each other. So you don't have the same voltage on both plates. V is maximum on the positive plate and 0 on the negative plate. A difference in voltage between top and bottom plates. That sounds good. Let's look at some charges moving. Nah, you don't have to have charges moving to have a field. Photons moving between the top, no. Okay, so it's the difference in voltage between the top and bottom plates causes that electric field, I guess. Okay, this is a good one. A positive charge is placed between two oppositely charged plates as shown. So there's my cue. Which way will the charge move? Well, duh. Positive charges always move along the field lines or from plus to minus. So in this case, it'd be down. It's the strength of the electric field. Okay, so that's E. What is the strength of the electric field at point B? Well, it's uniform, so it's going to be the same. Okay, outside of the electric field, outside of the parallel plates, you don't have any field due to the capacitor. The field stays inside the capacitor unless you hooked it up with a wire, which they didn't yet. So it's 0. Okay, so here's a charged object. Let's say it's positive. It is not going to move. It is not going to experience a force, electric force, and move unless there's a charged object next to it or near it. So this will experience a force. But to have that force, there'll be a repulsive force from here pushing in the same direction because the negative plate. So there has to be a voltage difference in order for it to move. So a difference in electric potential. You could also figure it out from an equation. Okay. Work equals the change in U equals Q times delta V. So work also equals electrical force on an object moving at some distance in the field. So The force depends on the delta V. The electric force depends on delta V. That's not really necessary if you just think of the logic out. Okay, I should have taught you this before, but there's another equation that's very useful for parallel plates. And that's V equals the electric field times the distance between the plates. So how did I get this equation? Maybe you don't care, but because E, newtons over Coulomb, is electrical force over the charge that's being moved. D is the distance that a particle could move from one plate to the other. Voltage is a change in U over Q. Okay, change in U is work. The work that the field does in moving the test charge. And the work is equal to electric force times the distance that's moved over Q. So look, these two equations, this proves that the voltage potential difference between the plates is equal to ED. So this is an important equation for parallel plates. So back to this equation. Back to this problem. Okay, so which has the biggest electric field? Which one has the strongest electric field? So using that equation I just put in the blue box, equals change in V over D. Okay, the D is the same in both cases. The delta V for B is 100 minus 0. Okay, the delta V for capacitor A is negative 100 minus 100, or 100 minus negative 100, which is 200 volts. So the guy with the bigger voltage is the bigger potential difference is going to be the one with the higher E. Okay, right? This is the same for both of them. The one with the bigger potential difference, the difference between the potential on both plates, is going to have the higher E. So that'd be A. Which generates the strongest electric field. Okay, again, change in V is plus or minus. I don't really care. 100 minus a negative 100 is 200 volts. Between these, 100 is the same, 200 volts, but the distance here is twice as much. So change in V equals ED. E equals change in V over D. The one with the smaller distance will have the bigger E. So that would be A. Okay, so we're changing two things here. This delta V is 300 minus negative 100. 300 minus negative 100 is 400 volts. This delta V is 200 volts. So let's just figure out E equals delta V over D. Okay, so this one is 200 divided by 0.1, and this E is 400 divided by 0.2. So that'd be 2,000 newtons per coulomb. This one would be 2,000 newtons per coulomb. So they have the same electric field. Okay, so you can solve this. They gave me the potential difference is 100. This is the distance. What is the magnitude of the electric field? Okay, so changing V equals ED. E equals changing V over D. So plug in your values. Change V is 100. D is 0.25. So that'd be 4 times, that's 400 newtons per coulomb. But it's also volts per meter, right? Because that's volts and that's meters. So a volt per meter is the same thing as a newton coulomb. Let's prove it. A volt is a joule per coulomb per meter, right? Joule per coulomb is what a volt is. A joule is a newton meter. And then I'll bring the rest of it. And so the meters cancel out, and I'm left with newton coulombs. So a volt per meter is equal to newton over coulomb. So you can use either one. Okay, so delta V equals ED. So 3,500 times 5. So calculating that, I get 14. Okay, this is worded a little differently, but work equals the change in U, right? So we have E here. Here's a little q that's accelerating, and here's the distance. So V equals ED. Change in V. Okay, so the change in V is also the change in U over the charge being moved. Okay, and I know change in U is work. The work you do is the change in potential energy of the charge. So that'd be work over Q equals ED. So what am I looking for? I'm looking for the work. So work equals QED. You could write this equation if you want on your equation sheet if I didn't put it there. So the charge is 6.1 milli coulombs times E is 300 newtons per coulomb times the distance, 0.20 meters. And I get 0.37 joules. There we go. So this is kind of confusing. So these are the electric field lines. And so that would be, field lines always go away from positive to negative. So it's uniform. So it's between two plates. Okay, so work, let's just use that equation we just did. Okay, the E is the same, the charge being moved is the same. Now, to simplify this, let's say the electron started on, on the negative plate and ended on the positive plate. This means the change in U, the change in potential energy, is the same for either, the same starting and the same finishing place. So the work is the same for both. The work done by field to move this charge, it doesn't matter if it moves sideways at all, because moving sideways doesn't change the potential energy. So if you had a particle like this and you moved it like this way, perpendicular to the field lines, that would take no work because there's no change in the potential energy of that charge. Okay, it's like, here's a bookshelf. Here's a book. You slid that book over here. It didn't gain or lose any potential energy in sliding it from one side to the other side of the bookshelf. Now, if you pushed it up to another shelf, it gained potential energy, or it dropped down to another shelf, you would have lost potential energy. But so work is the same for all paths shown.